Hello, this is the course of data structure and algorithms, and I'm glad to be with you again. And this is the course about the sorting algorithm, and we are going to learn about the merge sort. And this concept of merge sort use the PowerPoint material that has been given by the author of the book, Goodrich, Tamasya, and Goldwasser. So the agenda of this video will be about the divide and conquer, and yeah, this will be the basic definitions for all things about the sorting algorithms. We are going to discuss about merge sort and the analysis about the merge sort, like the big O and something. So what is merge sort? Before we do the merge, before we explain and before we learn more about the merge sort, we need to understand the idea about divide and conquer. So the divide and conquer is a general algorithm design paradigm. Okay, we call it this is the design paradigm because yeah, it has the idea to divide. Okay, so we call this is divide. So it means we want to divide the input data S into two disjoint subset S1 and S2. So we have one problem. So we want to divide into sub problems. Okay. And then recur, it means we want to solve the sub problems associated with S. S means the input data or the list, okay, or any set. Okay. So it can be anything. And yeah, we have the sub problem. We want to solve this one. We want to do the solution to the sub problem, and then finally we want to conquer. Okay, so I guess some literature they use not divide, recur, conquer, but they use divide, conquer, and combine. Yeah, basically they're the same. So the conquer means we want to combine the solution for S1 and S2, and we want to put it into the S. As you might know about the recursion, it is based on the recursion. So the base case for recursion are subproblems of size 0 or 1. In this kind of idea or in this kind of design paradigm, the divide and conquer can be used for the merge sort. So what the merge sort is a sorting algorithm based on the divide and conquer paradigm. And yeah, I don't explain about heap sort, but in the heap sort it will have like O and log n. Yeah, I guess some of you you already used the heap. I'm not sure how can you get that one, but yeah, it's a good practice for you. We can use heap to design the sorting algorithm. Unlike heap, so the merge sort, it does not use any auxiliary priority queue. So the heap sort, it uses the priority queue. If you still remember the priority queue, I guess yeah, you can easily understand later about the heap sort. So it accesses the data in a sequential manner. Yeah, you know the priority queue. Yeah, you can have the selection, and you can have the sequence listed and the unlisted sequence. Okay, so that the two kinds of concept you already learned from the priority queue. If you want to just insert, and then you don't put the sequence or you don't do the ordering at the first, yeah, when you search, it will take like yeah, O(n) power 2. But if you are doing the sort at the first time, so after any values entering the array and then you sort directly, yeah, it will have the O(n), and then if you want to search, another n will appear. So basically they are the same, but the way to solve the problems a little bit different. So that's the concept of the heap sort. That's the concept about the priority queue, and we can use this priority queue idea in order to sort. But I don't want to explain more the details of heap sort. We just focus on the merge sort, since the performance analysis of merge sort and heap sort is quite the same. So Using one of them will be just good for you. Okay. So the merge sort on an input sequence S with n elements consists of 3 steps. Okay, there are 3 steps. First is divide. As I already explained to you, we want to partition S into 2 sequences, S1 and S2. And yeah, it will be like n power 2, n divided by 2 elements. So the recur means it is recursively sort S1 and S2. Yeah, you want to sort the S1 and then you want to sort S2. Okay. And then if you just keep dividing, then you want to sort from the smallest element. After you have the sort of the smallest element, you will concur, in which you want to combine. So you want to merge. But the simple algorithm is somehow written in this pseudocode. So you can have the input and then you have the output, and then if the size is greater than 1, you can just do the partition. And whenever you do this partition, you will do the merge sort S1 and you will do the merge sort S2, and finally you will do the uh, merging for S1 and S2. So the merge sort is this one. Okay? So it means like the recursive, you will just keep looping until the last one. Merging two sorted sequences, in this case, yeah, you will need to merge those two sequences based on this one. Okay, so the important thing in this section is about the merge sort. So this merge sort is the loop, the recursion. Okay, so whenever we have a new element S, okay, we will check if the size is 1, then we will do partition to S1 and S2, and then do the S1. So after we do the S1, it means we will go to this recursion. We will do the S1, and then if S1 is greater than 1, then the S1 will be split into 2. Okay. Again, S1. So if the S1 is not the leaf node, then again we will do the merge sort, and then again we will do the partition into 2. Okay, and so on. And after you have all those small elements, you need to merge. So the merging will take place on 2 parameters or 2 sequences. So the sequence A and B. And yeah, after you do the merge of A and B, you will get the sorted sequence A union B. So it means A and B are combined together. The way to merge is something like this one. That the S is the empty sequence. We want to check if not empty for A and not empty for B. If A is the first element and if the A first element is less than B first element, then let's put let's remove the A and then let's put the A dot first into the last one. Okay. If not in this case, then let's put B. Okay. What does it mean? So you maybe it's better to show you with the example. Okay, so this is the merge sort. So we have S as merge function. We have S1 and S2, and we have the original S. So whenever we have the I plus j is less than length of S, then you will do this one. So you will do the, now if j is the same with the length of the S2, or if I is length, if the less than length S, and if SI and divide is less than S2, then yeah, you can do this one. So the Si plus j equals to Si. So we want to copy the I element of S as the next item of S. And the same with this one, we want to do the element of S2. Okay. I guess I will use another code to explain about the merge sort. Okay. So this is the merge sort. The idea is the same with the sort that you already learned. The basic idea about the merge sort, it was from the chapter 3 of chapter 4 or something like that. And yeah, if you were making the merge sort, you need to know first about the length of the list. Okay, so in this case s, and then if n less than 2, then return. So it's already divided. But if it is not less than 2 for n, then you can have the mid equals to n divided by 2. Do you know what is divide? Okay, yeah, divide. Okay, that's the division to get the integer value. So I want to go from 0 to mid, and then from mid to n. So the S1 will be from 0 to mid, and the S2 will be from mid until n. And then you do the sort S1, sort S2, and then merge S1, S2, and S. So the merge sort tree, it is an execution of merge sort which is depicted by a binary tree. Do you still remember what is binary tree? Okay, binary tree is a tree that consists only two children, left and right. Okay. Each node represents a recursive call of merge sort and stores the unsorted sequence. So we have the unsorted sequence before the execution and its partition, and then it consists sorted sequence at the end of the execution. Okay. Now we can say this one, the root is the initial call. Okay, so this kind of tree may have similar characteristic with the other tree, but they're different in some cases. Okay, so the leaf or the root, yeah, the root is the initial call, and the leaves are calls on subsequences of 0 or 1. Okay. So yeah, we want to do the subsequence. If it is like 7, 2, 9, 4, then yeah, if we take only the first two, so we have 7 and 2, and then we want to just give the each element to find out whether they are the same or not. Okay, and after they are the same, then we will do something to upgrade into the list. So let's see this example. Let's suppose I have I have 8 values, 7, 2, 9, 4, 3, 8, 6, 1. So if you want to do for first time for this kind of uh, sorting with the merge sort, you will do like this. So I want to split into two. So the S1 and S2. So this S1 will go to the left first. And because we are just dealing with the first half, okay, so 7, 9, 7, 2, 9, 4, then I want to check if we can just again cut. Okay, so the 7 and 2. So the result is, yeah, if you split one more time, the 7 will be just 7, and then the 2 will be just 2. Then we can put those two items, and we just say it is according to the um, type or something. Yeah, you get the 2 and 7, and then you will do the next number, which is 9 and 4. Yeah, so in the 9 and 4, well, again we want to check, okay, if the 4 is less than 9, then we just put 4 and 9. Okay, and after we have the value, okay, this is the value, and then this is the value, what happened? Yeah, it is the way to control this number. If you check this one, oh, where is it? Mm, um, so here, it mentioned that if you have a list, then yeah, you can do something that is related with this one. When you have blank or you don't have any idea, but you know that those two values are 9 and 4. So with this kind of divide and conquer, we have the 2, 7, and 4, 9. Of course, it is not in a sequence. Yes, you remember, if you remember on the the chapter. Yeah, there's one chapter about this kind of queue. This is the priority queue. Okay, so you want to know first two, and then you want to check with the first four. Okay, so which one is higher? So let's say we have 2, 4, and then 7. Oh, okay, maybe I don't put the 4 because it is too obvious. Oh, okay, then I will. So this, in this case, yeah, we do not do the result because it is only from the this bottom 2 and 7, and then 4 and 9. Then we need to have the priority rank between those two values, and let's assume that after you know the 2 and 7, it will go up, and then yeah, you will do the 2, 4, 7, 9. Okay, so it's like the one by one. You cannot just push all those numbers. And after you have the 7, 2, and 9, 4, we will do the next one, which is 2, 4, 7, 9. Oh, sorry, 3, 8, 6, 1. Okay, so this 3, 8, 6, 1, again, we split into the S2. So the split into S2 is the 3, 8, 6, 1, but if you are doing with the merge sort, then you can get the result like this one, 1, 3, 6, 8. So the 3 and 8 will be the same. So sorry, if 3 and 8, so yeah, there is no further changes because 3 is less than 8, then you can just use this. But the other number, which is 6 and 1, we know that 6 is x6 should be greater than 1, but in this case the 6 is before than 1. Then we can just replace them by giving the individual note, and then we want to compare what 3 and 1. Okay, so the winner is 1, and then next is 3, and then 8 and 6. Okay, the winner is 6, and the last one is 8. So finally, if you already have these two, okay, if you already have the 2, 4, 7, 9, and you have 1, 3, 6, 8, then you can put here. Okay, you can put here, and then the result will be something like this one. Okay, in the respective of the analysis, okay, merge sort is somehow we can check the head. Okay, what is the head? The head is this one. Okay, so I want to know the head of the merge sort tree. Okay, so the head, it shows the log n. Okay, after you do the log n for this one, at its recursive call, we divide the overall amount of work done at the nodes of depth I is O(n). We partition and merge to power of I sequences of size n power 2 of I. I don't, in this case, you don't need to confuse with the terminology. Okay, you just want to say that, and when you do with the height, okay, so this is the height for this what I call a binary tree. Okay, so the weight will not be so important because the head itself will consist of the partition. Okay, so when we do the partition, it will just create the binary tree with the head h. So h is using from the tree, and also from the graph how many tabs that you can get here. So the overall amount of or work done to the node tab I is O(n). So we just we want to partition, and we want to merge. Okay, and after we finish the statement, we just make the 2 power of I plus 1 recursive calls. So the total running is O n log n. So the log n here is the age here. If we have 8 data, then they just use 1, 2, 3. Okay, so they just have 3 methods to solve the problems. So you don't need to have a lot of access. You don't need to have the good computer. So just try, and then yeah, if you try, if you can apply with your own laptop, then no problem. Okay. So we already learned the selection sort and the insertion sort. Just to remember. Okay, the insertion sort, it means yeah, both of them, they are n power of 2, n power of 2. Okay. So the selection sort is like what you already learned in the priority queue. In the priority queue, you have the numbers. Okay, so every new number come, then it will be in the last. Every new number come, it will be in the last. Every new number come, it will be in the last. But we do not know whether those number are in the sequence or not. You can use selection sort. Okay. The time complexity is O n power of 2. However, yeah, some researchers mentioned that it is slow, and then it should have the in place. Okay, and for the data set that is more less than 1,000, 1K. Okay, 1,000. So yeah, if it is small, then small selection sort is good. If it is small, then insertion sort is good. But if the heap sort and heap sort take place for your analysis, I can say that the heap seed has kind of fast in place, and then for a large data set from 1K into 1 million. And then the merge sort that we already learned before, so it just split until the lowest element, and then we want to combine again. So the runtime takes O n log n. Okay, and please bring some material if you want to discuss with me about the kind of algorithm. Let's say yeah, you want to check the possibility to use sorting algorithms, and you just refer to this one. What is the sequential data access? Yeah, if you meet me, then yeah, you can just prepare all the materials, and then I can explain to you. And from the many analysis, yes, merge sort is very useful for huge dataset. So the huge dataset here means more than 1 million. But for the heap sort, it's about less than 1 million. Okay, yeah, you can yeah with the heap sort to handle the sorting, but of course there is yeah, there's no big difference between heap sort and merge sort. So actually you can use either. You don't need to use those two. Okay, now in the respective of the time, you can see that the variables in the first time that we learn about the priority queue, two of them are n power of 2. It means you cannot blame someone because it is n power of 2. But using this information, many people try to figure out how can we reduce the time performance. That's why heap sort comes and the merge sort also comes. And with this kind of idea, you can also do with your team project title. Let's say, yeah, you are going to do the matrix. Yes, I remember. Yeah, one team tried to do the matrix multiplication. Then yeah, you can say something that the algorithm A for this matrix, it takes O n power 2. The algorithm of A matrix B, okay, so let's say we have the matrix A and then matrix B. So I can like guessing, okay, if I use this algorithm, it will take how many hours? It will take how many hours? Yeah, those kind of things you need to put it into the consideration. And then for the heap sort and the merge sort, it is like the solution to reduce the time. Okay, so you can see that n power of 2 has been reduced by the heap sort and the merge sort, and it's just lower. Okay, so this one is lower. because we have the n log n, and this one this is also lower because we have n log n in comparison to the other algorithm. Okay, so yeah, that's all for this video, and I hope that you learned something about this merge sort, and we will continue with the other video which is still related with the sort. And yeah, feel free to ask me any questions, or if you need to have more discussion with offline, then you can just visit my office. Okay, thank you very much for listening. See you on the next video.